Hello and welcome to my dining room. Kind of terrible that I have to look at my own face on this stupid screen rather than a nice group of students, but that's the way it is. So what you don't know is this is like the fourth time I've done this, so it's like take four. But anyway, what I decided to try to do is make little 15-minute or so modules of little lecture bits and post them on Blackboard. So let's see how this goes. All right. So I'm going to go to OneNote here. And I'm just going to set my computer up a little bit so that I can do this little module. I'm calling it Module 1 because it's the first one I'm recording. And what this one's going to focus on is why there's such a huge variation in reaction rates. That some reactions are very slow and some reactions are very fast. So there's this huge range of reaction rates. And the question is why. So what I'm looking at specifically is I'd like to sort of focus in on second order reactions. So for example, where the rate is equal to the rate constant times the concentration of two different reactants. Suppose we're talking about A plus B goes to products or something like that. Okay, so this rate constant, which by the way has units of per molar per second, these rate constants can range from like 10 to the minus 8th to 10 to the 9th. And the question is, why is there this enormous variation? Okay, so that's what I'd like to focus on right now. So in order to understand this, we have to kind of understand what's going on in a chemical reaction. What has to happen? So, and in particular, I'm talking about a second order reaction, which has this rate law and is in general requires a collision between two molecules. So what has to happen when you have a reaction that requires a collision is, number one, you have to have a collision. So a collision must occur. But there are a couple of other things that have to be true and have to happen. The second thing is that the collision must have the proper orientation. And I'll go through an example to explain why this is. And the third thing is that even if you have a collision where the two reactants are oriented properly, you still very well might not have a reaction. And the reason for that is that there's a certain energy that is required for a reaction. And we aptly call this the activation energy. Okay. So I'm going to talk about these sort of, okay, so what this is showing here on the left is the ClNO2 molecule. So I'm really focusing on this reaction right here. And it's reacting with NO, okay, ClNO2 plus NO. And these are the three things that I already talked to you about. And so here are the reactants. Right here. And you could see that what's going on here is that this N and this Cl are going to form a bond with each other. And this is showing the electrons that are going to form the bond. That's what that arrow represents. And you could see down here, if you go a little further down, that the bond, this is the bond that's forming. So it's clear from this picture that the N from the NO has to be pointed directly at the Cl from the ClNO2, or this reaction just isn't going to happen because this N is not going to form a bond with the O here or this O here, and this O is not going to form a bond with that Cl. There's lots of wrong ways for these two things to approach each other. So this is the correct approach or orientation. And this is the only way that it can form that will lead to a reaction. But here's a couple of wrong orientations that I can show you, okay? So here, you know, with the one above, I had the NO oriented like this, and the N was pointed directly at the Cl, but this is showing what happens if the O is pointing directly at the Cl, and you'd basically get no reaction because it's the wrong orientation. And there's another example down here where now the ClNO2 molecule is flipped around and the O is trying to react here with the N of the NO. And again, this is the wrong orientation. And so there will be no reaction. Okay.